Hey everybody, and welcome back to Algebra 2 Online. So today we're going to do a little bit more with just specifically circles and ellipses. And there's going to be a few characteristics of ellipses I really want to take some time to talk about. I'm going to show you the definition of an ellipse and show you a few important facts about another major characteristic of them, which is these things called the foci points. But to start, this is going to kind of pull from some stuff from way back when we did quadratics. But a lot of times what you might see is equations written like this, and you need to know what conic section that is in order to maybe graph it or do something else with it. And so here, I want to find the center of this conic section and then graph it. And basically what you have to do when it's written in this form, this is not like our standard way that we write them. You have to complete the square in x and y, and we did this a long time ago. But once we complete the square in x and y, we'll kind of turn it into a form that we're more used to. So with completing the square, remember you can basically just group all the x terms, and then we're going to group all the y terms, but we can leave the number alone. So really I'm just going to write x squared plus 14x, and then plus y squared plus 6y equals negative 50. And when we complete the square, right, we just add b over 2 squared to the x squared and the x term, or b over 2 squared to the y squared and y terms. That's going to be different for each x or y thing here. But, and if you want to review on completing the square, definitely go back and watch that video. There's a ton in that video I'll explain about why that is the thing that we have to add. But in this case, what we would basically add is the following. And so we're adding this 49, again, just because it's 14 divided by 2, 7, and then squared 49, and then the 9 is being added because it's 6 divided by 2 is 3, and 3 squared is 9. And we add these just so we basically don't change anything, right? If we're adding something to the left side of an equation, we just have to add something to the right to balance everything out. So this is the exact same thing as this, but now you have the nice result where everything's going to factor. So you can multiply to 14 and, you can add to 14 and multiply to 49 if you do positive 7 and positive 7. And so that's my perfect square there. And then I can add to 6 and multiply to 9 if I use 3 and 3. And so my perfect square here is y plus 3. And then if you just add up everything on the right side, you're going to get 8. And so now this should look like a conic section. And we know it's just a circle, right? So this is just a circle. It has a radius of the square root of 8 and a center of, negative 7, negative 3. And so, if we were going to make a quick sketch of it, let's call that negative 7, let's call this negative 3. If you do the square root of 8, we know it has to be less than 3 because square root of 9 is 3. So this is probably 2 point something. I don't know what it is, but, we know that it's not going to cross the x-axis then. So, oops, that looked like it was about to cross. So, I'm just doing a bad job with the sketch. Okay, so this is my center, and then let's do that. Probably something about like that. So that's a rough sketch of this conic section. All right, so ellipses. There's definitely some important stuff I want to talk about. But to get started, I just kind of want to do a quick reminder on this piece. So there are two types of ellipses, right? We can kind of have a left-right one and a vertical one. And it's basically all tied to these a and b values here. And so if your number down here is bigger, so if a is bigger than b, then it's basically being stretched more in the x direction But if B is bigger than A, then it is being stretched more in the vertical direction. So you basically get, either an ellipse like that, or you get an ellipse like that. And one thing we didn't talk about before is the definition of an ellipse. So an ellipse is actually the set of points in a plane such that so these are the points in the plane, right? Such that the sum of the distances from two fixed points is constant, okay? So basically what that's saying is no matter where you are on this ellipse, right? The sum of the distances from the two fixed points is constant, and the two fixed points we're talking about are actually, for this ellipse it would be roughly here and here, for this ellipse it would be roughly here and here, but basically these distances are the same. So if you literally add up that distance, it's the same thing as adding up, we'll do one over here, this distance plus this distance. If I do another one, just to show you, let's say we're here, this distance plus this distance is also the same as the green stuff and the blue stuff. And these center kind of pieces here, these are called the foci, is plural for focus. So those two points there are called the foci. Some people say foci, but I've always said foci. But they're basically the 2 points that we're using to measure these distances that I'm talking about, okay? And you can actually do this with a piece of paper. You can have two fixed points like pins in some paper or something, and you can put a string around this, and then you can pull the string out tight, and if you just keep the string tight always around and around and around, you'll basically get an ellipse. That's a way to kind of see it, but that is the formal definition, and that's going to be important in what we're about to do on the next thing here. All right, and so we're going to use that because there's these two formulas that pop up, and they play a role in the definition of a ellipse that we just talked about. So just to kind of get started, so there are two axes for ellipses, okay? And the focus points will always appear on the larger axis, so you can see them right here and here. And we call that the major axis, so pretty obvious name. So this bigger axis is the major one, and then the other axis is just the minor one. So minor is smaller one, and that won't have the focus points. Major is the bigger, has the focus points, okay? And there are these three measurements, A, B, and C, that are part of an ellipse, and one of them we've talked about. So A is this measurement that is the stretch factor kind of left and right, and B is this measurement right here that's the stretch factor up and down. C is another measurement that is what we define as measuring from the center of the ellipse out to the focus points, right? And this distance and this distance are always going to be the same thing. And there's a very important relationship right here. And you do have to kind of know these two. Luckily, they're very similar, but it's saying that the distance from the center to a focus, if we square that, it either equals a squared minus b squared or b squared minus a squared. And I'm going to show you actually how this works, but just so you kind of see, so this is this has to make sense. We're not going to have c squared equaling a negative number. We're not going to deal with imaginary numbers here because we're talking distances. So this is a case when we have actually this one, right, where a is bigger than b, so this c squared is greater than 0. So I'm just going to put that up here. C squared is always greater than 0, so basically no imaginary numbers here. And so this is one where c squared would equal a squared minus b squared. But if you have, say, this kind of ellipse, then that's going to be the other one. That's going to be the b is bigger than the a, and so you're going to have c squared equals b squared minus a squared. Right? So what I want to do is actually just prove to you just this one. And the proof for this one is actually very much the same kind of thing. It's just not really worth going through. So remember the definition of an ellipse, right? It says that any point, like take this point or something, that this distance right here has to be the same as, or sorry, if you add these two things, right, that distance has to be the same as, let's do like green. So this, say, vertex over here, so this distance plus this distance, right? That one's kind of overlapping, but this plus this has to equal this plus this, because any point on the ellipse, right, that's the definition, is that wherever you are, the distance to the foci is the same. So here, this distance is the same as this distance, right? So I'm going to use those specific measurements. So let me make this a different color, actually. Make this like, so we're going to do that point, and we're going to make this blue. I think that'll be a little bit better. So we're going to make, we're going to use these two points to kind of help me relate A, B, and C. And I'm going to do that, and I'm going to show you that c squared equals a squared minus b squared. So just to kind of put some letters to this, I think, I'm going to call this point P up here, and then I'm going to call this point Q down here. And what I basically just drew out is, let's actually also call this focus F, and then we're going to call this focus F prime. Okay, so just in terms of like geometry here, we're saying that P to F, that distance, right, plus P to F prime has to be equal to QF plus QF prime. And that's really just the definition of an ellipse. That's all it is, okay? So let's use just normal Pythagorean Theorem kind of stuff and start filling some things in. So PF is part of a triangle, right? That's right. Let's do this in, what color have I not used? Purple. So there's a triangle right here, right? And we can basically get PF in that triangle, right? Because we know this is C, we know this is B, right? So if you use Pythagorean Theorem, PF is going to be the square root of B squared plus C squared, right? It's just Pythagorean Theorem. C squared plus B squared is PF squared, so we square root PF and square root the other side too. So this is my PF, and then PF prime, okay, is really the same exact thing, right? Because, you know, this purple triangle I just drew could be, I didn't do a very good job on this side, but this is a bit better. But this distance PF prime is also square root of B squared plus C squared, just using Pythagorean Theorem, okay? So really, this whole side is 2 square root B squared plus C squared. And so that is just what these two things basically are in terms of distance. Then, so QF, let's actually do this. So QF, if you look at the picture, Q to F, right? So this is C. This whole thing is A, right? So Q to F is A plus C. So I'm just going to literally write A plus C, all right? And Q to F prime, okay, we'll do this in yellow. So this little distance, right? This is A, this is C, right? So if you just do subtraction, the little piece left over is A minus C. So QF prime is, what did I just say, A minus C, okay? And so now I'm just I have some relationship between A, B's, and C's, and I can just go ahead and simplify everything. So, So I'm just going to simplify the right side first. So A plus C plus A minus C is going to leave me with just 2A, right? These cancel. The 2's also cancel. And so I get square root B squared plus C squared equals A. And so A squared is B squared plus C squared. And if you just look at the way I wrote it here, I just wrote it in terms of C squared. So C squared, if you move the B squared over, is A squared minus B squared. And that proves it. So it really is just a good thing to see that this is not some magical little formula, but it really just comes out of the definition of an ellipse and a little bit of like Pythagorean Theorem stuff, okay? These things play a role in a lot of our problems because we can use them to find the equation of an ellipse, okay? And I want to show you what I mean. All right, so what we're going to do here is we just have a picture of an ellipse, and we're just going to write the equation of it given the picture, all right? And if you look carefully, all we have is we have a nice point up here, 0, 9, and we have a foci, one of the focus points that's in a nice spot too. And other than that, though, this left-right distance, some weird, negative 5 point something number there. That's not going to be super helpful. It is centered definitely at the origin. You can see that. So that's nice, right? And actually, some of that means then that we can just go ahead and start filling some stuff in. If it's centered at the origin, then basically, with the x and the y squared stuff, we would just have like x minus 0 squared and y minus 0 squared. So that's kind of helpful. The left, right, the A measurement is not going to be super helpful, but we do already have the B, right? If you look at this, right, B has to be 9. And that means that under the y part, we always put B squared, right? So this is 81, right? Because we know that, from the last video, we can square root this number and get B. And so this is just 81. We're basically setting this thing equal to 1 in our heads, right? Because we just want to find A and B, and then we'll be done. And so A is the one thing, A that's going to go in here is the one thing I need to know. What is that value that I'm going to basically square and stick in there? And it comes out of using the thing that we just talked about. So we know the distance from the center to a focus is C, right? And so if you just, see, you can look, no pun intended, you can see how big C is. So these are all by ones, right? 1, 2, 3, 4, 5, 6, 7. So C is 7, right? And so if I just use that little, formula that relates A, B, and C, we would use C squared equals B squared minus A squared here, because we've got one where the B is bigger than the A. And so we know C is 7, we know B is 9, we want A, right? And so we got 49 equals 81 minus A squared. And so A squared is equal to 32. And really what we do is we really are plugging in the squared value there, right? We saw in the last video that if you square root these numbers, that tells you how far to go. So this distance right here, this one, is really the square root of 32. But what we put in the equation is actually just the 32, right? And so that would be like the best way to basically write the equation of that ellipse. And that's a good example of where we use this kind of formula. Very handy thing to know. All right, so this next question seems like a lot, but I think if you draw a picture, it starts to make a lot more sense. So basically it's saying that, so this is a geeky Star Wars question. So basically on Coruscant, there's a park called the Ellipse, and I'm just making all this up, but it's between the Jedi Temple and the Senate. And the park is surrounded by a path that forms this ellipse. That's why they call it the ellipse. And the length of the major axes is about 1,502 feet, and the minor axis is 1,280 feet. And suppose the park manager, Boothby, and if you know Boothby, you're a nerd. But say this guy wants to install water fountains at the two focus points, right? So the foci of that ellipse. So I want to find the distance. The question is find the distance between the fountains round to the nearest foot, let's say. So if you kind of turn this into a picture, I think it's a little bit easier to see what's going on. So we've got some sort of park where there's like this path that's moving an ellipse, okay? And there's definitely, two focus points. And that's where my water fountains are going to be, all right? And the question is basically, how far apart are those to the nearest foot? So we want to find the distance between the water fountains rounded to the nearest foot. And some things you were told. So the minor axis, right, this one, so that axis is 1,280. The major axis, which is the one that has the foci points, is, 1,502 feet, okay? And so it's another question, this is tied to B in some way. This is tied to A, right? And the actual question is tied to C. And so it's another problem that relates A, B, and C. And so we need to figure out which one of those we can figure out, which is A and B. And then we will, from there, find C and use C to tell us the distance between the two water fountains. All right. So we are going to start with just figuring out what A and B are. Let's do that. So 1502 is actually, right, 2B, right? So B, if you divide it, it's 751, right? Because B is just the measurement from the center up. So we have 751 and 751. Likewise, 1280 is 2A. So A is 640, if you divide that. And we have one of these ellipses that's more vertical. And so we are going to use the C squared equals B squared minus A squared. We need to know C. We have B, though, 751 squared minus 640 squared. We also have A, right? And so C squared is 154,401, right? And so this tells me that C is about 392 feet, and then there's like a decimal here. It's like 0.94-ish. But C is really just this distance right here, right? And we want to know the distance between the water fountains round to the nearest foot. And so what we really want is 2C, right? And 2C is about 785.8 or something. And so to the nearest foot, it would be 786 feet. That would be it. So the water fountains in this park are about 786 feet apart. All right, just going to do one more question here. And this one seems kind of weird, but it's actually pretty quick. It says, write an equation of an ellipse that has the same center as this conic section, okay? but it appears in every single quadrant, okay? So first thing we're going to have to do is definitely get the center of this, right? So it's kind of like going back to the first kind of question. We're probably going to have to complete the square, right? Because we can see we actually have a perfect square in x. We don't have any other x terms, so that's a perfect square. But we'll have to complete the square on the y stuff in order to get a perfect square there. So what I'm going to do is I'm going to divide by 25 first, just to make it a little bit easier to complete the square here. So if I divide by 25, right, I'll have that. And then I'll have y squared minus 4y, and then 125 divided by 25 is 5. And so remember, we don't really need this 5. We can move that over. And so we're basically just going to need to complete the square on the y stuff. So we're going to fill something in there. And we don't need to complete the square on the x stuff because that is a perfect square, right? We don't have any other x terms or something that are throwing me off and making it not a perfect square. So all I need to do is fill that in. And, same thing, b over 2 squared. B is negative 4, so negative 4 over 2 is negative 2. You square it, you get 4. And so we got to add a 4 on this side in order to balance this thing. And then we can actually find the center of it. So this thing factored is just y minus 2. And so I got y minus 2 squared in there, and then this is 9. All that we needed with this was to know the center of it, right? So it turns out it is a hyperbola, right? Because we got a negative term here. So this thing is a hyperbola. But we really just needed its center. And its center is, there's no shift there, but there's a shift 2 here. So we have 0, 2 is the center. And so I just need to write an equation of an ellipse that has a center of 0, 2, but it's large enough to be in every quadrant, right? So here, let me draw this. So center at 0, 2 would be right about there. And we basically just want an ellipse that has, like if I do it, just do like a vertical one or something like that. If we want it to be in every single quadrant, right, then we just need to make sure that the ellipse has got a and b values that are really, really, really large, right? Because as long as they're really big and going to get me out of, like, beyond 2, right, I can get to these quadrants down here or something. So you literally have tons of right answers. You just want to write something down that has the same center. So let's do that. So x squared, and then we've got y minus 2 squared. And then you literally just want a and b values that are really, really, really big to make sure that it stays and enters every quadrant somewhere. So you can just do something like 9, 9, 9, 9, 9. That's a huge a value. And then we could do 9, 9, 9, 9. And we just don't want to do the same y value, same like AB stretch. So we're just going to do like 8 or something like that. So this is an ellipse because these are different numbers. And for sure this thing is big enough to enter every quadrant. And it has the same center as that one. And so that does it.